briefly. Okay, so I'll leave it to you then.
All right, awesome. Let's see. I'm not visible here. Okay, cool. Everyone can take it up. Hi, everybody. We have some people in the room. We got some people online. This is great. Thank you everyone for showing up so soon before fall break to listen to me go on about climate science. Now then, I'm going to go ahead and start sharing a screen here. Okay, everybody see that this one? Let me see if I can get this into a good single page view here. Okay, now we're.
Yeah, yes, well, I think there's.
All right, so everybody online see just fine. All right, great. And it looks like we have a screen coming down behind me, so soon everyone in the physical room will be able to see just fine. Okay, awesome. Now, what I'm going to talk about today is, well, right there in the title. Why is California on fire? Because this has been a problem for quite a few years now. Now, I myself am not from California. I'm actually from South Florida, like get routinely destroyed by hurricanes, Florida. So why on earth am I writing about fires? Well, for starters, hurricanes are a lot harder to deal with. Secondly, because it's a very interesting problem. It's very relevant. If California were to separate from the US, it would be the 5th largest economy in the world, exceeding Great Britain's. So let's start, shall we? 2020, just last year. California fire season, most destructive on record by a huge margin. Over 2 million acres were burned. The largest fire of that year, the Camp Complex fire in Northern California, destroyed over 1 million acres on its own. Estimates of cost are still up in the air because it's so staggeringly high. 2021 meanwhile came along, severe heat wave, severe drought, very start of the year. Normally, California's fire season extends from about June to about now-ish. But as a result of the very, very extremely dry and hot spring climate, things started burning around April and still have not stopped. So 2020, we had about 2 million acres. 2021, we're already looking at about 2.8, with a much larger associated loss of human life. 2 people just straight up dead as a result of fires. Who knows how many dead as a result of fires on top of COVID. Now, these fire seasons are expected to become more active in the future. What? What would cause that? Now, this question is a little bit deeper than I might seem, because to some of you, the answer might seem like, oh, obviously climate change. But why? How do fires interact with the climate? And on top of that, a lot of what we know about the future climate shows that things like wind that drive fires when they're strong are really slowing down. So when I thought about presenting this in front of Math Club, I realized like there's so much climate background that goes into it that why don't I start by really talking about the science? Because when you're working in an applied domain, knowing about that domain is something key. You need to be able to formulate questions. You need to be able to know how to use the tools that you have as a quantitative scientist. So that brings to mind our next question. How on earth do we do science for this problem? Now, traditional statistics and traditional science relies kind of on this experimental scientific method, where you formulate hypotheses, you kind of have a statistical model already in mind when you start an experiment, and then you collect data and work from there. So things are controlled, things are nice. You can say nice, clean statements. Now, obviously, we can't really start a wildfire experimentally. They're kind of out of control by definition. But there's still lots of data available. We have satellites, we have all sorts of other things we'll get to in a second. So can we look at this data to get some information? We don't have nice things like IID or well randomized that we set up when we design experiments, and all sorts of other big important questions. The answer to all of these? Absolutely. Now, let's talk about statistical inference. So there's really kind of two big statistical camps. You have designed experiments, which is more so what you see in biostats, like a clinical trial setting, where you say, okay, here's exactly what we're going to do. All of the nice mathematical framework has been laid out ahead of time. And then you have, okay, here's sort of a natural experiment almost. It's different degrees of natural experiment. It sounds like economics, they consider things differently. But in our case, what we want to really do is take some data that was spat out by a process and then go backwards from there, try to figure stuff out about the process. Now, this is in contrast to purely predictive inference, which is what you see in fields like machine learning. In those cases, what they're trying to do is, here's what the process is spitting out, let's see what's going to come next. What we really want to do is build kind of this representation, idealized representation, if you will, of the process that made the data come out. Now, this generally involves statistical assumptions. Assumptions are not a bad thing. Assumptions give us a lot of power in stats, and that's one of the reasons why design experiments have been so successful at pushing science forward overall. Because we can say things about independence, normality, we really, really tighten the bounds on any uncertainty that we have. Now, making sensible assumptions in general requires learning about the process that we want to learn about. Also, we need to do. Now, part one, fire data. What is it? Where does it come from? This isn't something that I really thought about before I started working with atmospheric scientists. Like, where do we actually get this data from? You just kind of assume, like, oh, there's these antennas everywhere that, like, pick up what's going on with the weather. But first, I want to think about fire. What makes a fire good? Well, fire science itself is a huge and well-established field of scientific inquiry, and one of their particular subfields is something called pyrogeography. Now, what they deal with in pyrogeography is kind of the distribution of wildfires across space and across time. And they break things down into sort of three major components. These are the three things that make wildfires tick. These are the three things that they live and die on. And those are consumable resources. This is what the fire burns through. Now, if we want to look at consumable resources from a statistical standpoint, that means we're pretty much looking at vegetation. That's cool. Looking at vegetation is awesome. I'm a huge plant fan. Downside, finding data on that is really, really hard. The only good way to do it is pretty much to get a biologist, a bunch of grad students to go tape off a whole area of forest and go catalog every single thing they find. And then by the time you have those results, it's probably slightly different. You also have satellite imagery data, but that's bad for other reasons. In fact, here's one such other reason. So I didn't talk too much about this photo earlier, but I said island up there. That is Vancouver Island in British Columbia. This is the entire western half of North American continent, underneath a gigantic smoke cloud. And clouds make satellite imagery hard. Also, it's just a north amount of stuff, right? So back to our components of the fire regime. So really hard to get data on this, not the best thing to try to measure. Ignition, this is what starts the fire. Now, this is usually recorded. If you go and look at like USGS fire logs, they'll usually have like, oh, it was lightning, oh, it was someone out flying around with lighters. It was gender reveal party. But in general, it's not a huge deal. This typically doesn't have a big effect because fire's not really going to get out of hand unless it has somewhere to start from. Or if fire starts and it doesn't have the conditions in place to get out of hand, then it's not going to get out of hand. It's going to burn out and nothing's going to happen. Now, the third big component of the fire regime, and fire regime, by the way, a little bit of a vocab word, that's essentially like just the distribution of fires in an area. It varies on regional and time scales, but like for the Western US, for instance, it burns very quickly and frequently. So atmospheric conditions. What's happening around fire? Wind, how fast is it? Where is it coming from? Humidity, how dry is it? How dry could it be? And temperature, how hot is it? All these are things that seem like they might have influence towards the fire. And in general, they do. Now, to get information about these things, we can look at climate data, which, as it turns out, is very available. Now, let's talk about climate. What is it? Well, it's the thing that we live inside of. Now, weather is sort of what's happening outside right now. So if we look out the window, we see weather happening. And then climate is sort of what the weather is usually like over some region and some time. It's sort of, you take these individual local effects and you average them out over space and time. And that's what really gives you a climate. So you can talk about climate at all sorts of different scales. So for a regional scale, we might talk about like the climate of South Carolina. On a global scale, we might talk about Earth's climate. So how do we measure that? Now, the first thing is sort of that nice, I wish this were everywhere data, station data. Now, this, you can actually see a weather station right there. That is what collects your local weather data. When you pull up on the radar, like you notice how they've got those specific locations set up where it shows you the temperature in those studies. That's because these things are there, and that's neat. What these instruments do is they consistently record things, generally at fixed intervals, usually daily, sometimes a few times a day, and this is the closest thing to observational weather data that we have. Now, the problem with these, well, there's a few problems. Let's start with the good things. So pretty much everything I just said, especially if you're looking at a highly populated area, like let's say you want to do some research on the weather in LA, you have lots of station data to work with. If you want to look at station data in, I don't know, Kenosha, Wisconsin, you've got like 2 stations for more than twice as much area. So the more you get into kind of the untouched wilderness, the more sparse these weather stations become. On top of that, a lot of them are very, very old, so not all of them even have digitized records. So you might be calling somebody up in the Midwest, asking them to like recite to you what happened rain-wise on certain days in the 1980s. Now, a lot of organizations are in the process of digitizing, but right now that's still a problem. They don't all measure the same things. Like if you're looking for wind, you might have like 100 stations in a state. 10 of them have ever measured wind. Everyone else just looks at rain or something. Yeah, data quality all over the place. These stations are also split into multiple networks. Like you have a NOAA, the Northern Oceanic Atmospheric and something association. They're one of the big data collectors, but you also have like a state-run organizations. You might have other national organizations that are collecting weather data for other reasons. You have private industry that collects weather data for their own reasons. So it's kind of fractured between all the different things. There's no good centralized source, but again, great, powerful observational data. Now, let's talk about the other extreme, GCMs. A GCM is effectively a global climate model. It does not stand for global climate model. You really, really would think it would, but here we are. No, it stands for General Circulation Model, and this is kind of your very hardcore computer-based physics climate data. What they do is they take a snapshot, like this is what the world is like at this time, and then they just run a hideous gaggle of PDEs built off of Navier-Stokes, fluid dynamics, trying to account for all kinds of crazy interactions. And in doing so, they generate effectively simulated climate data like, hey, based on physics, which we know to be true, this is what's going to happen to the climate after a certain point. Now, the thing is, they're very, very good. Now, simulated climate data is very, very high quality. And it can be adjusted at any spatiotemporal resolution. So as with station data, we have kind of this uneven spacing problem where we might have a weather station here, a weather station over there, a weather station way over there. So when we try to do math, it's like, hey, we want a grid or a lattice. You don't have that, you have points. This can be done at any resolution, any shape, any time period. You want to go into the future, no problem. Now it does have problems though. The biggest problem, which might be obvious, is that it is simulated, it is not real. And physics is complicated. There's also lots of different paradigms for these climate models. And what that means is you'll usually run into different problems with different ones. For example, some climate data I was working with recently, we were trying to compare 2 models. One of them had very, very sort of low average wind speeds across the period we were looking at. And then with the other one, you had very low average wind speeds, but very high variance. So the end result ended up being roughly the same. The distribution was all over the place. It can also be very sensitive to initial conditions. So remember how I mentioned that this is a blob of PDEs effectively? PDEs need boundary conditions. It's sort of like how ODEs need initial conditions, otherwise you have an infinite solution set. With PDEs this complicated, you need to give it kind of a starting state, like this is what the climate is like when we start moving. And then you need all sorts of other crazy parameters and boundary conditions. And the result is you can get very, very finicky with how you tweak and adjust these models. And that's both kind of a blessing and a curse, because you can get really into it, but at the same time, you have so many parameters, you're more likely to be wrong at least somewhere. And once again, beautiful thing, we can look forward with them. So this is what lets us look at projections. And computational costs, they're very expensive to run. Very, very expensive. And again, now relatively new. They were just developed in, I believe, the 1980s when the first PCMs came into play. And then there's a few other kind of in the middle miscellaneous sorts of climate data that we can look at. The first one is satellite imagery. I kind of talked about this earlier, but it's getting away a lot. Still can be good data. It only captures a very broad resolution though. So like if you're interested in plant life in an area, you can like see where all the green is, but you can't really pick out like red flowers, purple flowers. So it's kind of limited by its own resolution. It's limited by who's taking the photos. Still, it can be extremely useful because it captures stuff in remote areas that's visible, but might not be recorded anywhere. For example, fires. If area burns, then satellite imagery is usually the best way to capture the fact that something burned down there. NWS, numeric weather simulation. It's basically a local GCM in a sense. Sometimes it's actually parameterized by GCMs, but the general idea is that you look at weather, which again is a local thing, and you think, okay, well, what's going to happen tomorrow? And this NWS is kind of how our weather forecasts are set. They're done on sort of this local basis rather than a regional one or even a global one. And then we have STAR, which I felt was worth including because it's statistically neat. These are statistical regional models. The idea is essentially bootstrapping, which in statistics means we sample with replacement to kind of shore up however much data we might be missing. So we look at a regional climate, we sample it, we sample it, we sample it, we sample it, we sample it. And from this, using good math principles, we kind of build up an approximation of what it's like. Now, all of these have their ups and downs, but the great thing is we can put all that information together into something called assimilated data products. Like satellite imagery tells us a lot about what's happening in the middle of nowhere. Cool. Station data tells us a lot about what's happening in big cities. Why don't we just take information from both of those and integrate them into one nice, clean data product? And right now, that's kind of one of the big bonuses in climate science is working towards these integrated data products that take in information from multiple sources to try to shore up their weaknesses with their strength. That's one example up there. So you can use station data to set those initial conditions for a GCA. And that's a very responsible, reasonable, and common thing to do. You can also use simulations to interpolate that station data and try to figure out what's happening in the middle. Usually what happens is a little bit of both. And we end up with nice sort of regular data products that evenly cover large areas of space and time and are very nice to work with. Now, in this fire case, we're certainly going to be turning to those. Now, we also need data about fires that we're going to try to answer the question. So how do we get that? Well, let's ask Happy Little Fireman. So there's lots of observational records, plenty of organizations keep track of them. Satellite data is another big source. Again, if something burned in the middle of nowhere, that's a great way to find it. And the US government has freakishly detailed records on this. And the big pieces of information that went from that generally are burned area, how much got cut down, when was it found, when was it contained. And again, there's point data. So a lot of that climate data, the way it's shaped is it's on a grid. So you can imagine you take a large area of space, lay the even grid on it, and then in every grid cell you have these climate conditions. And you get those like once every 3 hours or something. With fire data, it's just points. Like a fire happens, a fire dies. If you're familiar with stochastics, you can think of it as a point process. So that why earlier, not really a very good question. We've learned a little bit about climate, we've got some data. but we want to get really, really, really specific. So one way we can kind of address this problem is say, okay, well, actually looking into the numerical association between some climate process and these fires sounds really difficult. So one thing we can do is we take something that we know is well associated with fires, and then we look at modeling that instead. So that's exactly what one of the projects I'm working on right now is. So the Diablo winds of Northern California. Now, this graphic over here shows some fire data that I pulled. For Northern California, you can think right about here is sort of your Bay Area. Now, what is a Diablo wind? We actually see the Central Valley data. Now, some of you may have heard of Santa Anas. They're common in the news when we talk about Southern California's fires. Diablo winds are very similar, but they're a Northern California phenomenon. And the way it works is kind of like this. So up here, use the mouse that everybody can see. So kind of up here in this area, circling right now in this top corner. From there to about there, that is the Sierra Nevada mountain range. They are gigantic, heavy mountains in the middle of the country. Or on the west end of the country, I guess. Up here is something called the Great Basin. It is a massive, flat, bowl-shaped indentation in the ground that takes up the better part of 3 states. Above this Great Basin, there is something called an anticyclone. What that is a low-pressure system that exists way in the upper atmosphere and is just kind of constantly spinning, just lazily. And what happens is giant air masses will detach from that, and they'll start to come down and over the Sierra Nevada mountains. Now, what happens from there depends a lot. So some of them end up in Southern California, where they get forced through gorges and valleys and canyons and all those other features and get really, really, really fast and dry, and they just blast out over fires. Those are Santa Ana winds. What Diablo winds do is a little bit different. So they also come down over the Sierra Nevadas, but they come down over a much higher portion. And then when they fall, instead of falling into kind of these canyons that squeeze them and make them go really fast, they fall into this giant Central Valley region here. For those of you who have never been to California, that whole region is just like nice flat farmland in between a big mountain bowl, essentially. And when the air does that, it dries out a lot, loses an enormous amount of moisture. So then they go from there over to the coastal mountain ranges, which is kind of the other side of that bowl. And the coastal ranges are very tiny, very jagged, very tight, lots of ravines, lots of crevasses. They speed up there, kind of like Santa Ana winds do in the south and gorges, and they blast down slope. This is especially bad because of how fires work and how they interact with wind. Now, when a fire is burning, a wildfire specifically, something huge, wind has 2 big effects on it. Well, more than 2, but 2 big ones. Number 1, it physically moves it. A fire is going to run out of stuff to burn if it isn't moving. Wind pushes it. It drags the fire itself and it moves burning material, which are called firebrands, from the fire into stuff that is unburned. Now, this wouldn't be a problem if the unburned material were extremely wet. However, wind also moves heat from the fire, and in doing so, it dries out everything in front of it. So it's kind of this oven effect, which has been accompanied by lots of little flaming bits that go in there and put it. Anyway, it's not pretty. And downslope, both of these effects are terribly exacerbated. Firebrands fly further, and the air sinks faster. Now, what this project is looking at, these Diablo winds, also this last bullet here. So just to illustrate how extreme these winds are, the bare minimum threshold for us to consider something a Diablo wind is 18 miles an hour and has to blow for at least 6 hours consecutively. And that is with a relative humidity of under 25%, which is appallingly dry air, even by desert standards. And another thing these do is inhibit firefighting efforts, like helicopters and other aerial means of fire suppression are not really feasible if you have winds that severe going on. Now, these are not super well studied. The Santa Anas are much better understood, and again, the mechanisms of these are a little bit different. Now, what we see over here is a section of California, and this is actually a differential between Diablo winds in the last 20 years, and then during an end of century period from 2010 to, or 2084 to 2095, based on climate model data. The red is going up and the blue is going down. This is just raw frequency here. But the point is, if we look for the San Francisco Bay Area right around there, which is where lots and lots of people live, lots of tech companies, lots of other nice things, we see a pretty sharp increase, and that increase echoes across pretty much all the different dimensions that we're looking at, namely duration. We'll expect these ones to go much, much faster in the future if these climate models are going to go up, or much longer rather. So this is collaborative with my advisor, Dr. Wong. He's great. And Jolly Wong and Rao, I'm not even going to try that, of Argonne National Lab. And it was initially funded by PG&E as well, Pacific Gas and Electric. They are the kind of power company out there in Northern California. And that downflow thing is exactly what they were worried about, because they want to know, when do we shut off power immediately in order to stop more fires from happening? Now, intermission. Any questions?
I was curious about that anticyclone of the Great Basin. So it's more or less permanent, right?
Yeah, it's a enormous inverted trough. Actually, one of the big parts of the project was looking at that, like looking at upper atmospheric variables to try to explain the change we see. And one of our climate models actually showed it weakening really substantially.
What influences the permanence of that anticyclone? I mean, I guess the geography of the bowl is sort of, stuff dips down and you get a low pressure system, I guess.
There's quite a bit that goes into it. Scale stuff is definitely not my area of expertise. From my understanding, there's also a factor of sort of a constant upper atmospheric circulation where blobs of cold air detach the poles and then move south and north.
Okay.
It's quite a fascinating subject, though. All right, do we have any questions from the Zoom chat? All right, amazing.
Towards the beginning of the presentation, there was a point made about consumable resources, data which is hard to get.
Yeah.
So I mean, I know this simulation data might be hard to get, but if you would work on an analytical model like maybe some power law distribution or something. So one point I was thinking about was that the vegetation cover influences the climate, but then that is already taken into account because you're directly using the climate data.
Yeah.
But the distribution of the plants and the vegetation would also happen to have some influence on how the fire spreads. So I was wondering if that influence is greater than, I mean, how comparable is that influence to what the climate can influence the spread of the fire?
That's a very good question. And the answer is, one, it definitely depends. Namely, it depends on both the climate and on the vegetation and on that particular fire regime.
Yeah, the fuel of the fire will actually influence how long it goes on.
California is a particularly weird case because you have like 7 or 8 different major vegetation classifications that are all like layered next to each other going east to west.
Yeah.
So when you have those very intense winds like Santa Ana and the Diablo winds, and El Norte is another one that's much farther south, those blow through all the different regimes. So it's also kind of hard to keep track because fires don't really stand still.
Okay. One more is the sensitivity with respect to the initial conditions. So I get that since it's basically hydrodynamics, the climate study, that will be sensitive to the initial conditions. So it might create a big change in the climate, which will affect into the spread of the fire.
Yeah.
But I was wondering if a small change with respect to the overall climate would affect the fire. Like, is the spread of the fire also subject to initial conditions in terms of the climate?
So if you're trying to model a fire directly, yes, that's very, very difficult to do.
Because I would think that the randomness of it would not affect it that much. But in case of hydrodynamics, that's different.
it's not so much a matter of, well, there's lots of different sorts of randomness for the fire. One of the biggest issues of wildfire modeling in general, which we'll get to in the second half when I start talking about that, is non-stationarity. Wildfires are horrifically non-stationary, and for those who don't know what that means, when you're talking about a spatial or a space-time random process, if you want to look at dependence within that process, like what does this depend on as far as like where and when it's happening? If that depends on anything more than just like the raw distance between stuff, it becomes insanely hard to model. And stability under perturbation. So like if you're looking at PDEs, like how much does your numerical input actually affect it? It tends to be quite a lot because they have such a shape. Like fires burn in very non-uniform ways. Like they might lose their convexity, they might like channel themselves through little narrow things. It's a very hard problem to look at from a physics perspective, from my understanding. So, great questions, everybody. Thank you all very much. Let's look at how we're doing on time. Perfect. And let's look at part 2, which is where we start talking about statistics. So, as the question was beautifully segued into, fire models can't really deal with everything. They have a hard time with fires, and you can't really look at daily readings on a fire riskometer. Now, what climate models usually do when they want to project fire risk is they look at things like burn probability, like how likely is something to start here. It becomes really tricky when you look not at how likely is something to actually spark, but what's going to happen if we just have a fire here. Like, where is it going to go? What's it going to do? How long is it going to last? How much is it going to destroy before it can be put down? Now, a little bit of a segue back to the main stuff, but during the 20th century, there was a pretty big problem with fire suppression in the US. Namely, we did way too much of it. I don't know if any of you remember Smokey the Bear. Yeah, turns out Smokey advice terrible. If a forest catches fire, best thing to do, let it burn in general. It's the cheapest, it's the best. If we stop all those fires, what happens is you end up with this massive accrual of dead, dry biomass, which is just tender. So that's actually one of the big issues when it comes to California's current state, because those ecosystems are also built around catching fire and burning down periodically. Like from a biological, ecological perspective, a lot of plants and animals rely on those periodic burns. They evolved around them. That's just part of nature there. When we do things like put cities in a way that disrupts fires from moving, that messes things up in ways that are really hard to quantify. So looking at how fires interact with that environment, given that we've already kind of messed things up in at least that respect, becomes hard. Now, why does it become hard? So, the big issue here, non-stationary, as I just said, and the other one is kind of more general dependence. So this is where the question I was just alluding to. So if we start a fire somewhere, like let's say I just go out there with a lighter and light up an underbrush, what's going to happen to that fire if I just walk away and leave it alone? Well, there's lots of stuff that this depends on. So first of all, where it occurs in space and where it occurs in time. Now, in space, if I'm doing this at a dumpster in downtown LA, I might damage a couple of buildings, like someone's going to come by with a bucket of water and put it out. If I'm doing this in like an abandoned middle of a national forest, standing around a whole bunch of dead leaves, that's probably going to be a huge problem. I do not advocate arson. Now, in time, also a pretty big deal, because it's happening during the winter, it's rainier, then like you're more likely to have some water dumped on the fire, vegetation more moist in general. If it happens during, say, middle of summer, middle of nowhere, that's a particularly big risk. And that relationship between the fire and sort of its position in space-time probably isn't going to be the same for every single fire. In fact, when a fire gets bigger, you'd almost expect to see something different. Because like I just said about wind, the fire can dry stuff out in front of it as it moves. So when fires are huge, things like moisture don't really matter. The fire deals with that itself. Whereas if the fire's teeny tiny, like it is big, and trying to burn something full of wet, it's not going to do a good job. And also there are going to be some non-climate factors in play. So as I've alluded to a few times now, topography, huge. Mountains, dry fires. And also, what are some kind of quantitative challenges in modeling this kind of information? Let's watch, shall we? So this first bullet right here, it's a great quote. It's sometimes called the first law of geography. or Tobler's first law of geography. Everything is related to everything else, but nearby things are more related than distant things. Now, a lot of statistics, classical statistics, dealing with design experiments, rest on sort of IID assumptions. You want things to be independent, you want them to be identically distributed. Now, intuitively, independence means that one random variable doing something doesn't affect what the other one's doing. They're in their own lanes. Now, mathematically, what it means is that the joint PDF factors into marginal PDFs, but anyway, so spatiotemporal stems, because fires occur in time and space, we care about where they happen in time and space. We have no independence. Everything means the same, or everything is kind of influenced by everything. Like if a fire happens, a fire probably isn't going to happen right after because everything is burned down. The fire is probably not going to happen in like Antarctica because there's nothing to burn. So how do we model the space-time data? Well, what we really want there is the dependent structure. Like if we can kind of wrap our hands around that dependence, then we're done. At that point, it's just a standard statistical model because we can just take whatever we discovered and literally subtract it out. Now, separating out the effects of space and time isn't always possible. And that's another particular issue that's very unique to space-time data that doesn't exist in spatial data or time series. If you're familiar with time series in particular, you might notice that a few of the things I'm going to talk about are familiar in that context. So sometimes things depend on both space and time in a way that's distinct from how they depend on space or time individually. Now, what I mean by that is, let's say we're looking at, I don't know, let's go with just inland from LA, like Riverside area. That area in the 1950s and that area today are wildly different. It was nothing then, now it's crazy huge amounts. So sometimes you have this kind of non-separable space-time covariance that you need to account for, and by sometimes I mean most of the time. Now, another thing, reconciling different data sources. So remember earlier I said that it made sense to pull observational fire data and then reanalysis data, which is one of those assimilated data products called the climate variables. Those are different things. Does it make sense to work with both at the same time? Literally an open question. That's an area of very active investigation. From my understanding, it's a very interesting area too. And how much do we lose in terms of information by bringing the disparate sources together? And then can we quantify that much information? Those are rhetorical questions in most variables, and I don't think anybody does. So which climate variables to look at is another big thing for fire problems specifically. Now, two major factors once a wildfire starts: fuel moisture, fuel availability. Once the fire is huge, fuel moisture shouldn't matter as much in theory. So we're going to pull some climate variables from this mythical climate data set that I did not directly reference, but it's called the RA5 reanalysis. So we'll look at temperature, precipitation, relative humidity. What is relative humidity, you may ask? Well, it is the amount of water vapor in the air divided by the amount of water vapor that the air can potentially hold. It is a percentage measure, and you determine it using dew point temperature with actual temperature on top, because once you reach a certain heat, water will just start precipitating out. Now, we can also use vegetation cover data to account for fuel availability. So remember earlier how I said that data on vegetation is really hard to get? One thing you can actually get pretty well is data on just how much there is, just not what kind it is. So as long as we look at a relatively confined region, it shouldn't matter too much what kind it is, but that's all going to be at least kind of similar. So that's kind of spatial similarity working in our favor there. We know we won't get too many different kinds of plants right next to each other. And then wind, as I said, is a major contributor, so we'll run that in there as well. And this sort of list of covariates. Now, another big problem. Nobody cares about the average wildfire. Kind of like the average rainstorm. Nobody cares, it's just a thing that happens sometimes. Like, you move on with life. Average wildfire burns under 1,000 acres. Largest one last year burned north of 1 million. The big ones are the ones we care about. It's like, again, rain. Like what happened this morning? Hurricane. Ugh. The amount of damage caused by extreme events is disproportionate compared to just average ones, because everything's sort of built to deal with the average ones. Now, this concern sort of extends across many, many different climate factors. What we really care about are the tails, not the center. And now if you're taking a stats class, particularly math stats class, you know, there's a lot of stuff based around kind of means and central limit theorems and all these nice things. Let's talk about where the data is centered. Here, we don't care about that at all. We care about what's going on way over there in the tail. So I heard mention of power laws earlier. Here's some power law tips. So extreme value theory, what's that? This is how we deal with those tails. It is kind of a very nice general framework that uses some asymptotic results to let us deal way, way off in the right or way, way off in the left and look at the minima and maxima of statistical distributions, or of probability distributions, sorry. Now, this is a very big area in domain sciences in particular. I know civil and industrial engineering, it's very important. Climate science, obviously hugely important. Because, well, in civil engineering case, you need to build things to withstand floods that are bigger than any flood you've seen so far, or winds that are heavier than any wind you've seen so far. And you can't really estimate those by looking at means. You have to look way off in the tails using the specialized kind of map. So this sort of gives us a nice starting point in talking about what's happening far from the tails. And this graphic over here is something called the Pareto distribution. This is what you get if you set kind of a cutoff threshold for your values, like let's say a time series. Every time it goes above here, you want to grab that observation, call it extreme. The Pareto distribution is asymptotic with distribution of those extremes. It is extremely useful. Okay. Another problem. Well, right there in title. So, spatial dependence, as I just said, non-stationary. We care about a lot more than the distance between points in terms of the risk of a fire burning out of control there. Orography, which is the fancy word for how mountainous stuff is a big dealio. And it's also kind of hard to gauge how much distance and time matters because so, human activity. We affect the climate a lot at all sorts of different scales. So, locally speaking, it might be something as simple as like dumping water on a fire, like I mentioned earlier. On a more regional scale, it might be like we put a gigantic highway through a forest that is naturally meant to burn, like contiguously. Or on a global scale, it might be industrial emissions raising global mean temperature by an unreasonable amount. Now, disinformation campaigns sponsored by things like coal workers unions, ExxonMobil have been in the news since the 1980s trying to tell us there's no scientific consensus here. That is false. The consensus is universal. And also the effects of it are very difficult to predict because we really don't understand the thing that we've already started breaking. Now, things we've seen so far recently, a lot of these aren't that well known because they disproportionately affect very poor countries. Like the disruption of monsoon winds that is currently just ruining Burma's day. Unprecedented Atlantic hurricane activity last year's season was the most active since we started keeping records. Hurricanes depend entirely on sea surface temperature to sustain themselves. The start of ocean acidification. So ocean acidification is, CO2 is not just a greenhouse gas, it is also water soluble. We have put so much of it in the atmosphere that it is now dissolving in the ocean. Once it is in there, it forms carbolic acid, which, as the concentration increases, will become an existential threat to any marine animal with a shell, which is a lot of them. And also everything is literally on fire. Some things get really bad. We can see the collapse of oceanic and atmospheric currents, mass extinction of all those nice marine organisms I just mentioned, and anything that depends on them, sea level rise, polar ice caps melt, and even more extreme, violent, unpredictable weather. So it's likely to keep you in a job, but it's not the best thing for the world. Now, moving on from that. So we want to put a model together. And what we want to model is an association between two things. So a regression model is going to become a very natural, nice choice. Now, for those who don't know, a regression model is just saying, okay, here's some outcome that we've measured. We want to see how this relates to a set of other variables that we're able to measure in a way that's related. Now, what we want to do is interpolate. So what I tell my 1020 students is that extrapolation means where we're here, we want to see what's going on here. Interpolation is we've got points kind of here and here, we want to see what's happening in the middle. Now, with spatial interpolation, what that means is we want sort of a continuous spatial picture. We want to estimate the best one we can. Now, given that a fire exists at a certain point in space-time, how much area would we expect it to burn based on these surrounding climate conditions? Now we are at a good, focused, detailed research question. So, there's that regression model estimate. Now, note this is not a GLM, this is a regression model. GLM, we just had that epsilon there. But here, Y is a quote unquote response variable. In this case, it's kind of the area of these fires burn. X, beta. X is a matrix that we sort of make by gluing together all those other climate variables we care about one by one into columns. And then beta is a vector of, well, slopes, is one way to think about them. Those are things that we're going to be estimating. Beta is unknown. And epsilon is an error term that we assume to be IID, basically just a measurement noise, for lack of a better term. Now, this works if we don't have some weird spatial dependence at play. If we do, epsilon will not look right at all. We will have wonky residuals. The error term, sometimes called the residual term. No, we need to add another term to account for that space-time dependence. And we can do that with addition. Now, what kind of framework are we going to do this in? Well, we want something flexible and want to be able to account for things that we can't observe directly. And even if we can somehow figure out, like, this depends on this in this way, yada yada, how are we going to write that down? Now, everyone's favorite distribution, the normal one, except this one's slightly different. This is a Gaussian process. Well, not that, that's a picture, but a Gaussian process is a stochastic process. So what that is just a collection of indexed random variables. Now, what makes a Gaussian process special is that any collection of these you grab, you can pull them out of anywhere from just the infinite stream of randomness. Any finite collection will have a multivariate normal distribution. And the mean and covariance matrix of that multivariate normal will be governed by a mean function and covariance function that we can associate with the Gaussian process. So why on earth would we do something this complicated? After all, we are working with something infinite dimensional. This is very different from just dealing with kind of a finite collection of random variables, even if we allow those to depend on space and time. In fact, that's just kind of a realization of that process. No, GPs are nice to work with for a lot of reasons. Number one, we can talk about covariance functions. And sometimes it's a lot easier to encode your intuition about how something is behaving in terms of function than in some arbitrary matrix. And quick note on deep learning here. So this is a little bit of a side, but for some of you who are particularly machine learning literate, you might be wondering, why on earth do we not just solve this problem that way? Well, spatial data, spatiotemporal data especially, because the dependent structure is so incredibly meaningful, deep learning just doesn't work that well. That's right, right? But if we're looking at prediction in that context, traditional methods like kriging just tend to kind of outperform it across the board. There was recently a large competition held where multiple data sets were given to multiple teams who all tried to do prediction using different methods. Deep learning got mastered. Although there are some very interesting new models that combine ideas from machine learning and deep learning with some of the deep hierarchical models that are useful in spatiotemporal stats. I'm not going into too many details here. This is all very hand wavy, and that's just to make this seem cool and exciting because it is. Now, also computationally expensive. Putting a deep learning model is terrible. No, we've also have some technical details, but an extra convenient kind of Gaussian process model is a Gaussian Markov random field. This is a graphical model. Here's a graph. It's over Germany. Everyone say hi, Germany. Now, what makes the graphical model so cool is that these edges and vertices represent dependence. So, like, spatial dependence obviously doesn't extend across unlimited range. Like, what happens here probably isn't affecting what's happening in, say, middle of Kentucky. And that's what this graph kind of captures. So, like, if here's South Carolina and here's Kentucky, they're kind of related. They got nothing between them, but like, we're not related over there necessarily. And this graph framework is useful for a lot of reasons. Number one, because it's kind of super duper intuitive to set up. Like, see how some of the areas more tightly captured, that means we have kind of more varied spatial field there. And also it gives the ADM people something to talk about. That's right, we're dealing with a dependent structure here. It is an abstract simplicial complex. We can talk about Stanley Reisner theory. We're not going to. Now, specifying the spatial field. So the graph represents space-time dependence. And these things are very easy to fit, very easy to set up, and particularly using a Bayesian hierarchical framework. So, quick math is that. Now, this is where things get a little bit mappier. This is for the analysis or PDE people that are in the room, or any people. So, we have a lot of different choices of the covariance function. And one super convenient choice is a match-sharing covariance function. If we choose such a thing, what we end up with is the solution of this stochastic PDE. Now, W here is a white noise process, and S is the spatial points that we're evaluating at. What is important here is not necessarily the specific PDE, also the spectral decompositions. So, what's interesting here is that we can approximate PDE solutions really, really fast. Fitting Bayesian models, conducting posterior inference, that's hard. MCMC is a nightmare when your model starts getting big. You'll just be trying to disentangle convergence for days and days on end. Well, you wait like 18 hours for it to tell you that it didn't work. And then you develop a drinking problem. No. Approximating PDEs, fast, easy, finite element method. We already have this kind of nice lattice. We have a PDE that we know solves into our statistical model. We can just do that. And that is done using a fairly new technique called IMLA, which I think is very, very neat. Anyway, back to the applications. So what do we get if we fit such a model? Well, this is another thing that I kind of worked on. I can't leave over a lot of details, but it gets much, much mappier than that. But what I think was kind of the interesting takeaway from it is that really, really big fires really actually do behave kind of differently than small fires when it comes to climate. Specifically, big fires, wind seems to matter a lot more. And it seems like the way that wind matters is inconsistent. Either fast winds throw the fire or they kill it. I'm not quite sure what it depends on, but it's still a neat result. So, other climate problems. I'm closing out some open-ended stuff. So, here's a few other things that are available to look at, and I think could be super interesting. Air pollution. The atmosphere is an active chemical reaction 24/7. You dump some nitrous oxide into the atmosphere, who knows what it's changed into a month down the line. So how do we measure it? How do we determine which pollutants are actually bad? How do we figure out where it's even coming from? So Pacific oscillation. Most of you have heard about El Nino, La Nina. It's not well understood. And it might go away soon, so probably good to look at it now. And intersecting statistical ecology, I think, are also really neat. Essentially looking at how the climate interacts with living things using highly quantitative methods. And this is a great area to work in. People are so wonderful to collaborate with here. And that's about all I wanted to say, although I guess I do have one more thing. Kind of in contrast to all the doom and gloom earlier, talking about climate change and the imminent death of everything. I don't know, I guess just optimism in general. Yeah, humanity's pretty amazing. Like, just look at where we were about 100 years ago. A lot of people believe that disease was a result of luminiferous nature, and just look how far science has come. So I don't think that it's really a bad thing. I think it's more kind of a call to action than anything else. And that is it for my presentation. Thank you all very much for listening.
Check the chat out there too, but are there any questions?
Chat is clear. Do we have any questions in this room? How about it?
Yes, I have a question, actually. So, I'm sorry.
Go ahead.
So the whole point of extreme value theory, if you look at the tails, you look at these very unusual events, right? These huge blizzards, hurricanes, et cetera, et cetera. And of course, by definition, they're way out the tail, and you try to predict, how often you can expect these. Now, if we break things, then these start moving in from the tails and converging, right? So how does that change the extreme value theory moving forward? Like, if 50 years from now, things that we consider extreme now are much more common, now you've got a different tail, right? So do people think about like this dynamic? I mean, what if your extremes are actually sort of slowly converging?
Yeah, that is actually a serious problem, because not only are more extreme events becoming more commonplace, but we're also seeing just kind of more variance in general. Like, we have no idea how long some of these tails could potentially get.
Right.
So a lot of estimates are definitely actually being redone. And again, we're considering a process over a period of time. Even when we have all these nice asymptotic results, all of that non-stationarity is a result of that overall warming trend. And because we don't know exactly what that implies, kind of messes with the amount of uncertainty that we have surrounding those estimates.
So I had one question and one comment. My comment was on this extreme statistics. Right? So you mentioned several cases of where extreme values are important. And actually, in my field that I come from also, there's a very significant problem for which the extreme values are important. So I come from material science and engineering. And for example, fracture of ceramics is controlled by the largest single largest. Doesn't matter what the averages are, what the mean are, medians are, it's extreme. And we struggle with it a lot for the reasons that you mentioned. But so that's the comment. The question was that, one of the ways to get some confidence in the models and predictions is to see if they can predict past events. So how successful have these approaches been in, say, for example, predicting the last year's the big fire in California, or some other big ones like that?
So as far as fire prediction, again, that one's particularly a tricky one. With climate models more generally, it's kind of hard to look at the well, you certainly can look at past with them, but one issue is that they were already, in general, set using the past as kind of their initial conditions. There's really not that much to compare them with. For fire predictions, though, as far as evaluating what is, it's sort of difficult to look at, just because there are so many different dimensions on which you can evaluate. Like the models that I've been playing with, even though they are in mathematical terms fairly advanced, they're still fairly simplistic just in terms of how multifaceted this natural process is. There are so many things that go into it. Like when you consider an extreme fire, how do you even know it's extreme? Like what if it burned a lot but really slowly? Like is that still bad? Do you go by duration? Do you go by burned area? Do you go by severity? Do you go by monetary damage caused? There's all kinds of different ways you can look at the problem. But in general, it's a very evolving area, especially as computers become more and more advanced and more people become aware of how to use computational science to try to solve these issues.
I think it was a good point in the talk too. I mean, I never really thought about this, I think, per se, but you think of a lot of famous experiments in science, like the Michaelson Morley experiment, milk and oil drop experiment, whatever. These are things that they collected data doing this in a very controlled environment. So it's a different sort of aspect of science when you've got to go out and get data that, who knows how dirty it is because it wasn't really clean in a controlled environment. That's kind of an interesting aspect of it.
Yeah, exactly. When you're doing design experiments, you kind of already have your statistics in mind. Like you sort of design the model as you designed it. So then it's a matter of if anything happens, the model will determine what's going on. When you're dealing with kind of data in the wild, you've also got to worry about picking a model.
Okay, other questions? Yes.
So, so you're looking at the effect of the wind on the fire. Right? So you mentioned that you have a matrix which takes into account different climatic variables. So, can you give me an idea of how many, like, what's the parameter space that you're dealing with?
So, the parameter space in this case, if we're looking in terms of dimensionality of the model matrix, the project I did with this was about 150,000 space-time points. And to each of those were associated a vector of, let's see, probably about 10 different planet covariates, as well as several time series.
Okay, All right, so I had a question regarding so you mentioned that we mainly focus on the big fires, like millions of acres. So this is a statistical study, but if I was to look at an analytical model, should I expect to get a similar solution with the scaling of the amount of area the fire is covering?
So if you're looking at a local model, you probably. So the way that fires occur as far as variance goes is very, very strange because once it gets out of control, it sort of feeds itself at that point. It's kind of like a income is actually a very similar distribution. The rich get richer. Similarly with fires, once they're huge, they'll merge with other fires, they'll blow. That's another big problem with fire. Sometimes they start in multiple places and they'll come together. So like which is even with fire. But so the distribution this takes on, you have a Pareto tail and generally something like a log normal kind of bulk of the distribution. And that's actually the exact model I used when I was looking at fires was this log normal Pareto mixture. And that's the same one that generally describes income because you have like Jeff Bezos out there with hundreds of billions of dollars in personal wealth, and then you have regular people. Like the difference is just astronomical.
Yeah.
So the fact you have kind of like this regular probability distribution, and then with sort of a fat tail tacked on, also really adds to complexity there.
And I think you might have a question in the chat.
Oh, let's see. Oh,
okay.
Asia.
So yeah, I have a few more questions.
Go for it.
So you said that the terrain that you're working with also matters.
Mhm.
So I mean, I would think that for a given range of sloping, and if you're dealing with, let's just say, trees in general, then the height of the trees will account for the sloping, unless we are talking about very different places like mountains and plains. But the fire spread that we get, let's just say on a hilly area and on a plain, how different are they?
That's really exacerbated by wind is the issue. So like if it's not
Yeah.
very windy, you would kind of expect a mountain fire to spread a little bit less.
Yeah.
Just because number one, the air is thinner there, that will start to matter after you reach a certain altitude.
Yeah.
Number two, also because nothing is actively forcing it down and the hot air wants to rise. Now when they're blowing down slope, that's really, really bad. And when they're blowing up slope, that's like actively killing the fire.
Okay. And regarding your interpolation scheme, what's the what's the scale over which you're interpolating? Because that should be important given if you're expecting, say, some extremums in the graphs, then the length scale over which you're interpolating should be important because you do not want to miss those points. So how do you decide on that?
So as far as the length goes, there's quite a few modeling choices you can make to try to account for that effect. Also, the biggest thing from like actually doing it standpoint is making sure that you're working in a coordinate system that isn't lat-long. Because lat-long, you're dealing with a projection, so really you're in projected space, your lines don't work quite right. But you also can't really use something like meters because then your numbers are so big, you run into numeric layers because of instability. So that itself is kind of an interesting bit of a related point. But no, as far as the spatial ranges, you can kind of sequester these meshes. So if we go back here to the mesh that I had pulled up. So you can kind of separate these meshes and deal with distinct ones, and that way kind of covers large branches. Because if you put another like fleet here and then sever all of its connections with this graph, those are just independent regions. And that actually does come up quite a bit if you're trying to deploy these models in a setting where like some of your area is over water and some of it is over land, for instance. This is particular element to work with somewhere like Norway. The guy again, there's Norwegian. But if you work with somewhere like Norway, you've got all these crazy complicated fjords, and like you know that whatever you're measuring is going to be very different here versus there. You end up with a lot of like weird independent little leaks in the model. So in that respect, the sheer size of the spatial domain doesn't matter much. What matters more is kind of the density of these nodes and just how well you construct your graph in general.
Okay. Yeah. Okay. Yeah. That's good. And last question, for the parameter space, did you try to reduce the number of variables using some process like SVD or something?
Like dimensionality reduction?
Yeah.
Not in this case, no, just because like there isn't that much motivation to do so. So remember when I said that you can solve these PDEs fast? You can solve these PDEs really fast. So like dimensionality reduction does become a bit more relevant when you actually have something to lose.
Yeah.
As far as regularization and model selection, within the specific framework I was doing, there were a few ways that I carried that out. One was by looking at CPO scores, which is a little bit tricky because cross-validation doesn't really do what you think it does. That, and then, what's the other one? BIC and DIC are both information criterion for Bayesian models that look at generalization out of sample error, and those are particularly applicable here. Or at least to this MLA scheme.
Yeah, that was all.
All right, thank you very much.
All right, let's take our speaker again. Well, I hope everybody has a fantastic break. We will have a back club after we get back. It will be in this room with pizza, but it will be given online. So anyway, you'll have a safe and fun break. We will see you all when you get back. Oh, and take a pizza. You are starving students, so.